Imagine effortlessly speaking to someone in a foreign language, instantly understood. This is the promise of real-time instant voice translation. And today we're peeling back the layers on the complex architecture that makes it all possible. Let's begin by grounding ourselves in what real-time instant voice translation, or RIVT, truly entails. RIVT is defined by the rapid conversion of spoken words from a source language to synthesized speech in a target language with minimal perceptible delay. Real-time is the key metric here. The complexity of integrating multiple AI components instantly is immense, but the need for RIVT systems in a globally connected world, from travel to business, makes this technology indispensable. Now let's break down the fundamental architectural components required for a functional RIVT system. The RIVT process can be segmented into 4 essential stages: speech input and recognition, machine translation, speech synthesis, and finally, delivery. The typical pipeline involves audio being captured, converted to text, translated, converted back to audio, and then outputted, all within milliseconds. This requires seamless integration of various high-performance models. The first critical hurdle in RIVT is accurately converting the spoken word into text, handled by the automatic speech recognition, or ASR module. ASR models utilize complex acoustic and language modeling to turn raw audio input into a transcript. This transcription must be highly accurate, as any error here is carried through the entire system. ASR systems must be robust enough to handle real-world challenges like background noise, different speaker accents, and varying speech rates, often requiring specialized deep learning models for pre-processing. Once we have the text, we move to the core process, translating the source language text into the target language, powered by machine translation. Modern RIVT overwhelmingly relies on neural machine translation, or NMT, typically using transformer architectures. These sequence-to-sequence models are exceptionally good at capturing long-range dependencies in language. Ensuring semantic accuracy is tough. The NMT engine must correctly handle context, slang, and idiomatic expressions, not just word-for-word substitutions, for a natural and meaningful translation. The translated text must now be converted back into audio, which is the domain of text-to-speech synthesis, or TTS. TTS modules take the translated text and generate natural-sounding human speech, ensuring correct intonation, rhythm, and stress to make the final output clear and conversational. Advanced RIVT systems might use voice cloning technology to synthesize the output in the original speaker's voice, adding a layer of familiarity and personalization to the real-time interaction. The greatest architectural challenge is achieving true real-time performance, which demands significant optimization at every stage. Latency, the delay between speaking and hearing the translation, must be kept to a bare minimum, often below 300 milliseconds, to maintain the feel of a natural conversation. Techniques like partial word prediction in ASR and segment-based translation allow the system to start processing before a sentence is complete. Buffering helps smooth out temporary network or processing delays. In conclusion, RIVT systems represent a masterful integration of cutting-edge AI technologies operating at lightning speed. As these systems become more seamless and accurate, the future of cross-language communication will be transformed, breaking down barriers and connecting us like never before. The sophisticated interplay between ASR, NMT, and TTS, all optimized for speed, is the hidden architecture that delivers instant voice translation to the world.